find out when you're doing problems like these is that there's more than one way to do it. Yesterday in class, we did problems like this, but we did them as they were side angle side. Right. This case here, it's giving you all three sides, but it doesn't tell you a similarity statement to know what matches out. So what I would do is I would revert back to the idea of the side angle side. I would not bother with those two segments that 44 and the 80. What I would do is I would wander through my narrative setup like I had earlier, and I kind of tilt my head sideways a bit so I can see how the angles work themselves out. Here's what I mean. Once we did in class yesterday, we're kind of like this. We're off to the side a little bit. Well, tilt your head. You'll be fine. Does everybody agree that angle L would be the shared angle between the small and the large triangle? Yeah. So if I go numerator, numerator. Numerator, numerator. By doing it that way, think of it in terms of the sides, angle side, it's a lot cleaner. Okay? And then I would just go ahead and simplify my fraction on the left, 1477 becomes 2 over 11 divided both by 7. So I would use 2 over 11 as my ratio, just because it's easier. If I cross multiply that, I'm going to get 132 equals 26x plus 2, and then just go ahead and solve from there. When you do 18, I think, Johnny, you were saying 18? 17? Okay. I think 17 looks eerily similar to that, and I hate to use the word similar, but kind of does. So when you look at 17, if you follow that same pattern, if you will, of thinking of it as a side angle side style problem, keep the small triangle segments as your numerator. Small, small. Large, large. And then just cross multiply it out. What I did earlier with this problem, I knew that I had to multiply by 121 coming over here. But what I did was I initially just simplified 65 over 143. Did enter, and then I multiplied that by 121. And I get 55 equals 2x plus 27. I thought that was a little bit cleaner of a way of doing it. Was it 28? You get 14, I think? Last one. 14. And again, this is that same idea that even though they're giving you all three side lengths, fall back and revert to the idea of the side angle side. Side angle side. 16 x plus 10, 28, 43. By going back to that idea, it just makes it easier. It's a lot cleaner, and there's a little bit less weirdness to worry about. Let's see here. This is what, 4/7, so 42 times 4 over 7, 6, so 24. 14 again? Yes, I am. No, what I did was I knew that these are both divisible by 4, so I got 4/7. And I knew that I could bring the 42 up here. 42 divided by 7 is 6. Or I can just press button. Make sure your name and set that up. Careful. So, number 5, I think it's easier to break it down into 3 basic formulas. And it is they're so unbelievably wordy that I think that is so much easier for us to just look at a diagram and see what happens. And you might be pleasantly surprised as if I explain it this way, it's a lot cleaner. For example, if I draw a triangle, and then I draw a segment inside the triangle that's parallel to one of the sides. That segment that's on the interior of the triangle doesn't necessarily have to be running into a midpoint or anything like that. All it has to be is parallel to one of the other sides. So it could be horizontal, it could be on one of the sides on the diagonals, it doesn't matter. But the general generic orientation of it then, how many segments are created on the sides of that one triangle? If you think about it, don't you have 1, 2, 3, 4 segments then? Think of this parallel line then as a fraction bar. Numerator, denominator, numerator, denominator. Think of that parallel line as a fraction bar. So if you see a diagram that has a parallel side to one of the sides of the triangle, that parallel portion on the interior of the triangle acts as a fraction bar for the sides. Think of it as a fraction bar. So if I'm looking at it in terms of a numerical example, I'll let you guys draw this real quick. So let me write this again. Think of it as a fraction. Top divided by bottom. Right? So when you have this numerically, it creates numerators, denominators. Here's what I mean. Here's what I mean by that. That KL is parallel to PN, which means it creates 2 segments on the left, 2 segments on the right. So think of this KL then as a fraction bar. See how easy that is? Yeah. It is so much cleaner, so much easier to look at, as opposed to all these god-awful words. Sometimes words get in the way. Sometimes the word has done all these long-winded definitions get in the way of something that can be extraordinarily easily explained by the idea that, hey, look at that, numbskulls. We've got a parallel side to another parallel part of a triangle. It makes a fraction bar. Do you think anything would change if this diagram happened to be rotated? No, what would you do? You just turn your head a little bit and go, oh, look at that. Okay. Cross multiply. 12x equals 9x plus 9. Are you guys okay with me skipping the distributive property there? Not by writing it, not skipping it, but not writing it out. You guys okay with that? Thanks, man. I feel you too. Subtract the 9x. You just said you feel me, and now all of a sudden you go, wait, which is it? Thanks, bro. Stop whining. Okay. I know it is dumb. It's a silly way of thinking about how these things work, but I'm telling you, if you see two parallel sides like that, just think of the one on the side of it being a fraction. It is the easiest way to do it. Okay. Try another one. I have a feeling you're going to be okay. With any luck, when you write this out, you wrote x over x plus 4. 12 over 18, that simplifies to being what? Let's make it easier. 2/3, very good. You don't have, do you have to? Nope. Cross multiply. 3x equals 2x plus 8. X is? Pace yourselves. What's wrong? Okay.
You just gotta say the answer.
I would hope so. That just means we did the right thing. Okay. So, fraction bars. Think of it, remember that. Here's another one. Sometimes in geometry, you will see multiple parallel lines. I know. So if I have 3 parallel lines, and 2 transversals, what do you think I'm going to say that middle parallel line is going to act as? A fraction bar. Whoa. Whoa. So again, if you see you have 3 parallel lines. Go away! Think of the middle one as a fraction bar. Now this one again, I drew it up where they were horizontal. Do they have to be horizontal? Nope. More often than not, they won't be. But just again, I just wanted to show you how the orientation can turn itself around. So you got 3 parallel lines intersecting 2 transversals. Once again, think of it as the middle one as a fraction bar. So here's your fraction bar of numerator over denominator, numerator over denominator. Denominator, if I can say the word correctly. This is very commonly seen. I tried to pull it up last hour, but the website was down. Have you guys ever seen plot lines in neighborhoods? Plot lines. So if you think about your neighborhoods, do you ever seen like the corner of your property? There's like a metal stake in the ground. So the metal stakes are the property line. It's labeled. It tells you where things are at. Newer subdivisions, they're easier to find because it hasn't been completely overgrown than it is on some of the older stuff. That's why you'll see people out there if your house is being sold and whatnot. They'll go out there with a what do you call it? A metal detector, and they'll look at the plot lines. They'll put a stake in the ground where it's at. Those plot lines are generally always going to be parallel to everybody's down the same street. Usually, obviously, when we go around a curve, not to be. More often than not, your plot lines will be parallel to your next door neighbors. Now, your front yard, your backyards could be wider out one way, could be curved up in the front, stuff like that. But that's kind of where you see a lot of these shown up. The DeKalb County Assessor's Office, people who do that process your tax bills and stuff like that, What if you look on their, this thing called Google Earth, it's pretty sweet. I know it might take off one of these. Google company's pretty good. It might take off one of these things. No, you guys joke. When Google Earth first came out, I'm telling you, we were like, oh my God, that's freaking awesome. It was nuts. You can zoom in and you see all this. You know, then when they go drive around the Street View thing, have you ever seen the Street View truck drive around? A few years. I have, yeah. I actually have. I was going home from school once, and I saw it drive by me. There's the Google car. So I kept pulling up Google, looking to see if they see me in my truck. It's got this big giant thing on this roof. Anyway, example. The Google car. Here's an example, not of the Google car, but of plots of land. You're right. I apologize. The violence between the two of you, I'm telling you. So again, think of it as the fraction bar, splitting it into a numerator and denominator. Does it matter which direction you tilt to figure out which one's on top or bottom? Not at all. So if you're thinking this, if I lean over like, okay, that's 62 over x, has to equal 56 over 70. Or if I look the other direction, oh, isn't that x over 62, which happens to be 70 over 56? It doesn't matter, and that's the whole point. It doesn't matter which direction you tilt to look where that fraction bar is being placed. Okay? It is the cheesiest way to do this, but it works. Okay? And it works. 56 and 70, they're both divisible by 7. You get 8 and 10. 8 and 10 simplifies to being 4/5. Yeah, so you get 4x equals 62 times 5. Divide that by 4. What'd you say it was? There? It is. That's what we got last hour. And remember, guys, it is completely, totally fine if you get decimals and fractions for some of these. It is not a big deal. I'll get the rest of it. Okay. Once again, ordinarily straightforward. The next one, though, you're really going to love. The next one you're really going to love. The reason why you're going to love it is because it's an angle bisector. So, why? What's so complicated about an angle bisector? No? Remember, when you have an angle bisector, all it does is bisect the angle. It is not necessarily running into a midpoint. It is not perpendicular necessarily to the side opposite. All an angle bisector does is bisect an angle, and if continued on, it intersects the side opposite. Are we okay with that? Now, the side opposite the angle bisector is now cut into two pieces. Gentlemen, stop. It is cut into two pieces. They aren't necessarily congruent. They could be, but we don't know. But what happens here is, if you really, really want to love this style of a problem, draw a arc.
I don't get it.
Because you love the slab. It is not a but. I told you there's no ass in math. It's a heart. Here's what I'm getting at. Here's a numerator, denominator. Numerator, denominator. When you have an angle bisector style, think of the angle bisector goes out and comes back. So you love it. Let me show you with numbers. There really isn't a fraction bar on this one, but watch what happens. You spin this so you can see it better. So you can see it better. Now, when you have this angle bisector, it's capturing the fraction. 15 over 25, 6 over x. Yes, sir. Yeah. You're going out, the angle bisector comes out, comes around. Numerator, denominator. Numerator, denominator. I'm just drawing a heart around it because I'm being stupid and crazy. Yeah. Go ahead. I just love this problem. You can flip it. If you draw your hearts bottom up. Either one. All I'm trying to show you is that no matter, as long as you're consistent, if the side that's being drawn to is the numerator, then the opposite, the other parts are the denominator, or denominator to numerator to denominator. However you draw it. Yeah. Yeah. Yep. Okay. They're just. I know it's really cheesy. Like really, 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 really bad. But that's why I'm trying to show you an easy way of writing this out as opposed to all the long-winded, god-awful definition words to it. So if you have an angle bisector, you have the angle bisector. Just love it. Okay. All right. Once again, cross multiply and solve. 15 25ths happens to wind up being what? 3/5, I believe. So you get 3x is 30. Rock a rhyme that's right on time. Every time somebody says that, it goes through my head. Okay. All right, try this one.
Say less.
Remember, it's really easy just to love it. Just love it. Just love it. It's so goofy when you draw hearts around it to show that you love what you're doing. But, you know, Valentine's Day is coming. What's that? No, all right. The math department has had smart boards longer than anybody else. We got the old building about 4 years before anybody else did. So, yes, I have been using a smart board for 8 or centuries. How old do you think I am? Shut up. You guys all fail.
Now you have more than 27 projects. Maybe like 32.
Because of what?
Because college.
Oh. So you get 10 over, if you draw the heart around it, you get 10 over 12, 18 over x. Do you have to simplify or can you multiply like this? It's either way is fine, it doesn't matter. Yeah, if you go 5 over 6, you have 5x equals 6 times 18. What'd you get for x? 21.6? It works. Remember, guys, it's okay to get decimals with these things. There's nothing wrong with that. It does happen. The weird style that can happen with this, though, is that, let me see if I can pull it. If I have it open. If I'm looking at, if I look at one like this, this might be as weird as this style problem gets. Ladies and gentlemen, I would suggest drawing the example or trying to jump to any conclusions here. Again, I would set it up to be the style that I love. Correct, because they're saying a bisector. So if I love this, my heart happens to look like lungs and or kidneys. Remember, ladies and gentlemen, so I apologize to the good artists in this room. I'm not. I'm sorry. I'll get over it. So watch what happens. You're going out and coming back in. X over 6. If this whole thing is 6, this much is x, what's left for here? Very good. It is a very common scenario for these guys. It's a very common scenario for this style of problem, whether it's with the heart one or parallel lines, that you're going to get the whole section and you have to subtract out the unknown. Happens all the time. It is very, very, very common. Right? So if the whole thing is 6, back out the x, you get 6 minus x. Cross multiply this one through, you're going to get 4x, 36 minus 6x. Add the 6x. You get 3.6. It's okay. Yeah, because if you're given the whole thing, you back out what you know. It's like from here to the door is 4 feet. I go 1 foot. How much is left? From here to the door is 10 feet. I go 2 feet. How much is left? 10. Okay, so what'd you do? So from here to the door is 10 feet. I go on an unknown amount. How much is left? Well, 10 minus the unknown amount. Same.
Did you just like leave at the bottom?
Yeah. I backed out.
Just subtract x.
Yeah. Yeah. No, not to get rid of it. Remember, if this from here to here is 6, from here to here is x. If I take this out, how much is left here? It gives you the side opposite. So this is 6 minus x. Coming out and around, 6 minus x over 4. That's about as weird as this is. For this evening,
What do we have, sir?
those. Now, remember, that trick shows up a lot. That trick like that shows up quite often. Make sure that you look for it.